Welcome everybody to the talk. This is a joint work with Louis Molitor and Pascal Lenzner from the Hasso-Plattner Institute of Potsdam in Germany and Vittorio Bilò from the University of Salento in Italy. My name is Davide Bilò and I work at the University of Sassari in Italy. The title of my talk is Topological Influence and Locality in Swap Schelling Games. In the talk I will speak about some game-theoretic segregation models. Segregation is a well-known sociological phenomenon. It means that a community of people which differ along several traits tends to segregate over time. Famous examples of residential segregation are many urban areas in the United States. The phenomenon of residential segregation has been first studied by Thomas Schelling in the 70s. In the model proposed by Schelling, there are two types of agents that occupy vertices of a line or of a grid. Some vertices can be left unoccupied, and each agent is either content or discontent. An agent is content if and only if the fraction of agents of the same type of the considerand agent that are in the neighborhood of the considerand agent is greater than or equal to some given threshold value. A content agent doesn't want to move, while a discontent agent either jumps to a random unoccupied place or swaps its position with the position of another agent chosen at random. By empirical studies, Thomas Schelling observed that if we start from a random board and we let the random process run, if the random process terminates, it often leads to a configuration with a high level of segregation, and this is true even if the agents are tolerant. The models proposed by Schelling and some of their variants have been validated via empirical studies, and some of them have also been studied as random processes. The concept of segregation has also recently attracted the attention of the algorithmic game theory community, and there are some papers that have been published recently in which some models of segregation have been proposed. The model that we studied in our paper, which is called the K-swap Schelling game, is the one that has been proposed and studied for the first time in the very recent paper by Agarwal et al. In the K-swap Schelling game, we are given a connected graph of n vertices and n selfish agents, each of which has a type which is an integer value between 1 and k, and each agent chooses an empty vertex where to place itself. Here is an example of a placement for the agents where there are 4 types of agents, where each type is represented by a color. Each agent has a utility in participating to the game, which, as in the original model of Schelling, is defined as the fraction of the agents of the same type of the considerand agent that are in the neighborhood of the considerand agent. For example, the utility of this agent here is equal to 0, while the utility of this agent here is equal to 1 divided by 4. And finally, agents are allowed to swap. So any two agents can swap their positions, but since agents are selfish, they do so if and only if, by swapping their positions, both agents improve their utilities by a strictly positive value. When such a swap event occurs, we say that the swap is an improving swap. For example, the swap that we see here is an improving swap because both agents improve their utilities to 1/2. Finally, we say that the placement is stable if and only if there is no improving swap. It turns out that the placement that we see here is stable. In our paper, we also defined a local variant of the K-swap Schelling game that we called local K-swap Schelling game. And in this variant, swaps are only allowed between adjacent edges. Since we are restricting the set of potential swaps, we have that any placement that is stable for the K-swap Schelling game is also stable for the local version of it. But the converse is not true in general. As I said earlier, the K-swap Schelling game has been first proposed and studied in the paper of Agarwal et al., where the authors considered a general version of the game in which there are also stubborn agents, where a stubborn agent is an agent that never wants to swap. Elkind et al. In this paper studied the K-jump Schelling game, which differs from the K-swap Schelling games for two aspects. First of all, the number of agents is strictly less than n, which means that there are unoccupied vertices in the graph, and agents are allowed to jump and not to swap. And agents can only jump to unoccupied vertices. Finally, in these two papers, the author studied a variant of both K-jump and K-swap Schelling games, in which agents can either be content or discontent, where an agent is content if and only if its utility is greater than or equal to a given fixed threshold value. But now let's move to the state of the art for the K-swap Schelling game and its local variant, and speak about the existence of stable placements and the game dynamics. In our paper we studied all the graph topologies that we see here. By 4 grids we mean standard grids, while an 8 grid is a 4 grid in which we additionally connect each vertex to its top left, top right, bottom left and bottom right vertices respectively, if they exist. Agarwal et al. Proved that there are two regular trees that do not admit stable placements. Two regular means that the difference between the maximum degree and the minimum degree is equal to 2. So for the class of trees and for the class of arbitrary graphs, we have negative answers for the general version of the game. Excel et al. Proved the positive results for both versions of the game and for the class of regular graphs. More precisely, stable placements are always guaranteed to exist, and in particular, the authors of this paper proved that if we start from any placement, then after a sequence of at most m improving swaps, where m is equal to the number of edges of the graph, we always end up in a placement that is stable. In the language of algorithmic game theory, this is equivalent to say that for the class of regular graphs, that the game for the class of regular graphs is a potential game. Clearly, cycles are regular graphs. So since the bad example of Agarwal et al. Was a two regular tree, it is natural to answer to the question of whether one regular graphs behave like regular graphs or not. In our paper, we answer affirmatively to this question and proved that one regular graphs behave exactly like regular graphs. Of course, paths are one regular graphs. Using similar techniques, we proved positive results also for the 4 grids. For the 8 grids, we have the existence of stable placements under the assumption that there are 2 types of agents. We know that the game may not converge to a stable placement in the K-swap Schelling game, but if we look at the local version of the game, then the convergence to stable placements is always guaranteed. This difference between the general version of the game and the local version of the game also shows up for the class of trees, for which we proved that stable placements always exist in the local version of the game. The most important open problem here is that of filling this entry here, that is, trying to understand whether any graph in the local version of the game always admits a stable placement. So let's now move to the results about the price of anarchy. Agarwal et al. In their paper proved that the price of anarchy can be unbounded even if there are 3 types of agents and the game instance is balanced. That is, there are exactly and divided by 3 agents per type. Because of this bad news, Agarwal et al. decided to focus their attention on the case in which there are only two types of agents. Unfortunately, the price of anarchy can be still unbounded even for trees, but this only happens when for a specific type there is exactly one agent of that type. If we exclude this not very significant case, and we can do so by assuming that there are at least two agents per type, the price of anarchy suddenly becomes bounded even for arbitrary graphs, but the bound can be pretty bad. If the game instance is balanced, that is, the number of orange agents equals the number of blue agents, Agarwal et al. Proved a constant upper bound to the price of anarchy. Actually, they showed that the price of anarchy is upper bounded by 4 and lower bounded by 2.05, although this lower bound here holds only for graphs with a few constant number of vertices. In our paper, we have improved the upper bound of the price of anarchy for the balanced version of the game and two types, and show that large enough graphs have a price of anarchy that is almost 2 in the balanced version of the game. This is not a standalone result, but it follows as a corollary of a more general result. Here is the updated state of the art for the price of anarchy bounds. As we can see, we proved several upper bounds and lower bounds to the price of anarchy for both versions of the game and several graph topologies. So on the left side we have the upper and lower bounds for the general version of the game, while on the right side we have the upper and lower bounds for the local version of the game. And since we know that any placement that is stable for the general version of the game is also stable for the local version of the game, we have that any upper bound that you see on the right side, so that holds for the local version of the game, carries over the general version of the game, and similarly any lower bound that you see for the general version of the game holds also for the local version of the game. All the bounds that you see in this table hold for the case in which there are two types of agents. So let's now see some interesting upper bounds and lower bounds to the price of anarchy. This is probably the most interesting result. It's slightly difficult to parse. By O here we mean the number of agents of the minority type. This is the result, the upper bound to the price of anarchy that holds for the general version of the game only. That implies that the price of anarchy is constant whenever the ratio between the number of blue agents and the number of orange agents is constant. Here is another interesting upper bound to the price of anarchy that holds for both versions of the game. So if we consider the class of graphs of maximum degree delta less than or equal to n minus 2, and we assume that, and we restrict to the graphs that admit stable placement, we have that the price of anarchy for such a class of graphs is upper bounded by a function that depends on the square on the maximum degree, and is also lower bounded by a function that depends on the square of the maximum degree. Another interesting upper bound to the price of anarchy is this one here, which holds for both versions of the game in the case in which for the class of graphs of minimum degree greater than or equal to 2. So here we are somehow including the class of 2H connected graphs. Whenever a graph in this class admits a stable placement, the price of anarchy for such a graph is upper bounded by the ratio between the maximum degree and the minimum degree multiplied by a suitable constant. Other interesting results are the following. So we closed the problem for regular graphs by providing tight bounds to the price of anarchy for both versions of the game, and we also provided refined upper and lower bounds to the price of anarchy for cycles, paths, 4 grids, and 8 grids. So now let's move to the technical part and provide some technical details. First of all, I would like to show an important lemma that we used extensively in our paper to provide the upper bounds to the price of anarchy. The lemma, other than being useful, can be considered as a standalone result because it provides necessary and sufficient conditions for stable placements in both versions of the game. The lemma states that the placement for both versions of the game is stable if and only if, for any potential swap of two agents of different types, we have that the sum of the utilities of the considered agents is greater than or equal to 1 minus a fraction whose numerator contains this Boolean variable adjacent, which is equal to 1 if and only if the two agents, considered agents, are adjacent in the graph, and the denominator is equal to the minimum of the degrees of the two vertices that are occupied by the considered agents. I'm not going to prove the lemma, but I simply want to show a couple of applications of the lemma. And here is the first example. So in this slide, we prove that price of anarchy of a local to swap Schelling game played on a 4 grid with 2 rows and several columns is almost equal to 3. To prove the lower bound that approaches 3 for large grids, it's enough that we show an instance of the game in which the ratio between the social welfare of an optimal placement and the social welfare of a stable placement approaches 3. So the game instance that we consider is the one in which the number of orange agents equals the number of blue agents. Here is an optimal placement. The social welfare of this placement is equal to this value here. And this is a second placement that stays stable with respect to local swaps. The social welfare of this placement is equal to this value here. Clearly, the ratio between the social welfare of the social optimum and the social welfare of this stable placement approaches 3 when the grid is large enough. To prove the upper bound of 3, we fix a stable placement and look at the agents column by column. Since the bound here is an upper bound to the social welfare of any stable placement, so the average utility of each agent in any placement is strictly less than 1, it is enough to prove the claim that we show that a border column contributes with a utility that is greater than or equal to 1/2. So the two agents that are at bordered column in the overall give a contribution to the social welfare that is greater than or equal to 1/2, while each other column contributes with a utility that is greater or equal to 2 divided by 3. The proof divides into two cases. So in the case in which the column we are looking at is occupied by agents of the same type, by simply computing the utilities of the agent, we have that the claim is trivially true. In the more interesting case, in which the two agents, the column we are looking at is occupied by two agents of different types, we need to apply the lemma. So, first of all, since the placement we are looking at is stable and the two agents U and B may potentially swap, we can apply the lemma. So the lemma states that the sum of the utilities of the two agents is greater than or equal to 1 minus the Boolean variable adjacent is equal to 1 in both cases divided by the minimum degree. In this case, the minimum degree is equal to 3, while in this case, the minimum degree is equal to 2. So in both cases, we have that a border column contributes with a utility that is greater or equal to 1/2, because 1 minus 1 divided by the minimum degree that is equal to 2 is 1/2. And in the other case, we have that a middle column gives a contribution that is greater than or equal to 2/3, because 1 minus 1 divided by 3, the minimum degree is 3, is equal to 2/3. Now let's see another application of the lemma with a second example, and we combine the lemma with matching techniques. Matching techniques are extensively used in our paper in order to provide upper bounds to the price of anarchy. So now I'm going to show how to apply the lemma in order to prove that the price of anarchy of the balanced two-swap Schelling game is upper bounded by roughly 2. Remember that the balanced version of the game means that there are as many orange agents as blue agents. So for the upper bound of the social welfare, we have that n-4n is an upper bound, and this is due to the fact that there must be a blue agent that is adjacent to an orange agent in any possible placement. And now let's try to provide an estimation of the social welfare of any stable placement. So let's fix a stable placement, like the one that we see in the slide. And let's start by computing a maximal cardinality matching of non-adjacent agents of different types. So the red edges form such a maximal cardinality matching. So we might be left over with 2x vertices, x over which are unmatched blue agents, and x of which are unmatched orange agents. And the nice property of the cluster is that each unmatched blue agent is adjacent to all the x unmatched orange agents, and each unmatched orange agent is adjacent to all the x unmatched blue agents, and this is due because of the maximality of the matching. So this implies that the minimum degree of the vertices occupied by unmatched agents is greater than or equal to x. And now we can apply the lemma. So let's try to estimate the contribution given to the social welfare by all the matched agents. So consider two agents that are matched by a red edge. Since by definition of the matching the two agents are non-adjacent, and since we are considering a stable placement, the value of the Boolean variable adjacent is equal to 0 for those agents. So if we apply the lemma, we have that the sum of the utilities of each pair of agents that are matched is greater than or equal to 1. So this means that the contribution of all the matched agents to the social welfare is lower bounded by the sides of the matching. And the sides of the matching is equal to n minus 2x divided by 2, which is exactly equal to n divided by 2 minus x. And now let's try to provide an estimation to the contribution of the social welfare for all the unmatched agents. So we match the unmatched agents using a second matching that is of green color. So again, we are matching agents of different colors. So since the game is balanced, the sides of the matching is exactly equal to x because there are 2x unmatched agents. And now let's see what is the contribution of each pair of matched agents with respect to the green matching. So since the two agents are adjacent, we have that the Boolean variable adjacent is equal to 1 for such two agents. However, we have also that the agents are within a cluster of minimum degree x. So the contribution of the two agents, the contribution that the two agents gives to the social welfare, the contribution that the two agents give to the social welfare is greater than or equal to 1 minus 1 divided by x. So in the overall, we have that n divided by 2 minus 1 is a lower bound to the sum of the utilities of any stable placement. And this completes the proof. This is the end of my talk. Thanks a lot for your attention.